This this test, the practice test that I assigned you, is I think particularly hard. Um, so I want to talk a little bit about some of these problems. Maybe I'll do a few problems in each video and post these certainly by Monday at some point. So looking at number one, the guidance counselor is looking at extracurricular activities and comparing it to GPA. And so the number of extracurricular activities a student participates in his or her grade point average is close to 0. So the correlation, if it's close to 0, means that we've got a scattering. So the number of extracurricular activities and the GPA really seem to have no correlation if it's close to 0. So students that do a lot of extracurricular activities have anywhere from a bad GPA to a good GPA, which is what this is saying. So the best answer here on this would be that no conclusion should be made based on the correlation without looking at a scatter plot of data. So basically, if we've got a correlation close to 0, you don't have a positive or a negative slope or anything like that to go off of. Unless our correlation is, let's see, not equal. If r is greater than 0.7 or r squared is greater than or equal to 0.5, these are both true. If one's true, the other is true. Then we can maybe start making some sort of an assumption about a student's the number of extracurricular activities in the grade. So this one's a no conclusion should be made. All right, number 2. So we've got calculator dependent students versus a paper and pencil method. And each student takes both quizzes, one with a calculator and one without, in a random order. To analyze the data, the students construct a scatter plot that displays the linear association between the number of correct answers with and without a calculator for the 30 students. A least squares regression yields the equation given here. Now, this r equals 0.79 that somebody underlined is probably something we're going to need. So which of the following statements is true? Well, if a student had used a calculator as the explanatory variable, the correlation would remain the same. All right, so is that true? So basically what this is saying is if we switch the calculator and the pencil, if we switch the graph from pencil to calculator and pencil, where pencil is the explanatory variable, to calculator and pencil this way, that will change a couple of things, but what it won't change is the r value. The correlations here are going to be the same regardless of which one you call x and which one you call y. So let's go back to 1. If a student had used the calculator as the explanatory variable instead of pencil, the correlation would remain the same. That's true. Okay. If the student had used the calculator as the explanatory variable, the slope of the least squares line would remain the same. No. I think perhaps I have some data here to show that. Sometimes it helps to just kind of look at some data. This is our Archaeopteryx data that we kind of use throughout sort of most of this little chapter. So I'm going to use L3 and L4, and I'm going to show you that if I calculate the line of regression using that data, L3 and L4, where this would be x and y, what I really want to look at is what's the slope, and that's given here in this b value. Slope is about 1.2. Now if I do the inverse of that, where I make the y the x and the x the y, is the slope going to be the same? By the way, look at the r value here. We can kind of verify that other. 0.994. So if I go back here to my data and I do my line reg, but I change my x and my y, let's see what happens to the slope and the r value. Now see, the slope was 1.2 and now it's 0.82, so that's definitely changed. But look, the r value remains unchanged. So it doesn't matter which direction we go there. So number 2 is false. The least squares line slope would not remain the same. All right, and the standard deviation of the number of correct answers on the paper and pencil quiz was smaller than the standard deviation on the calculator quizzes. This one is kind of the hard one here, because what we have to bring in is our formula, b equals r times s sub y over s sub x. So the standard deviation of the calculators over the standard deviation of the pencil times r. Well, that's why they actually give us r over here as 0.79. So if I take 0.79 and I multiply it times a fraction of calculator over pencil, what must be true about that fraction for that slope to increase? Well, I'm thinking that this number on top has to be bigger than the number on the bottom. So let's just try something. What if I made the calculator standard deviation 7 and the pencil 8? This is just number sense. So if I take that and I multiply that, I go 0.79 times a fraction of, oops, that's not what I want, 0.79 times a fraction, it's doing the same thing, times, there we go, I think that'll do it. Okay, a fraction of 7 over 8, I get a number that's smaller. There we go. I get a number that's smaller. So for the number to actually be bigger, the slope to actually be bigger, I must be multiplying by a number that's greater than 1. So let me just switch these. The 7 and the 8 are just numbers I'm pulling out of my head, just for the fun of it. I'm just playing with fractions here. There we go. So for that r value to increase, it'd have to multiply by an improper fraction, which would make the standard deviation of the calculator a larger standard deviation than the pencil. So let's go back to the question. The standard deviation of the number of correct answers on the paper and pencil quizzes was smaller than the standard deviation on the calculator quizzes? Yes, that's exactly what we found. So 1 and 3 are true.